Yeah, so hello everyone. My name is Ilya Segal and I'm a PhD student at Ruhr University Bochum. And today I want to show you an example how to construct a matrix for real, for something like a real data, but the data that we will be looking on is coming from the last year's International K-Matrix Day. But for those who didn't attend last year's K-Matrix Day, don't be upset or scared. I will introduce what was previously on K-Matrix Day and properly give you explanation of the problem. So everything that I will be doing, I'll do in with a Julia programming language, and we'll be showing you this nice Pluto notebook. So first of all, here I have some infrastructure. Again, don't be scared of it. There are some packages that we will be using. Also some plotting options and some service functions that we will need to treat the parameters of the feed. So the problem that we will be looking at is similar to what we have in real life. Let's imagine that we have some experimental data, some points, and we want to somehow approach it. And we need to parameterize the spectra. And we will do this today using the K-matrix approach, which needs already introduced to you. So let's extract our data, which I already produced using the results of the last year's K-matrix day. So it's stored in the CSV file. Let's read it. So if you want, you can also play with Pluto notebook. It's uploaded on our webpage, and also this data which I'm extracting now is there. So I called it experimental data, even though it is not really experimental data. This is data that I sampled based on the results of our last year's K-matrix day. So let's extract it and save in the data frame. So you see that in our data, we have some mass of our system and weights. So basically the mean of this mass. So let's plot this data. I'll clean it up a little bit. I already know the boundaries of our spectra. So let's set minimum and maximum of our masses. There's from 3 to 8 GeV. So we need to create a histogram. On x-axis, we will have our masses. Then we need to provide weights as well. And bin edges. In range from this min to max. And let's say that we want 40 bins. Well, it's loading. So you see that we already have histogram. Let's store our data in the name tuple. So make it easy to access it. So our bins will be just bin centers of this histogram, and our content would be bin counts of the histogram. For further plotting, let's introduce also bin widths, which will be just difference between the second and the first bin of our histogram, plus all the bins that we have are the same width. And let's also plot it, plot this histogram on the scatter to make it nice. So on the x-axis, we'll have m bins. And content on the x-axis. And also errors we will calculate just as a square root of our input data, the square root of our bins. Let's see if it will work. We will see a nice plot of our data. Yes. So that's what I produced from the last year's K-matrix day. And to remind you what we had there, at the last example, we considered the case in which we have only one channel, but with two resonances. So already Nils introduced to you what we are discussing here. So first of all, we're considering scattering of some particles A and B in the particles CD, and there is some intermediate state resonance with some certain mass M0 and gamma 0 can be produced. And in this case, we are looking at the data that was produced with such one channel, but with two resonances, so with masses M1 and M2, and with this gamma 0, gamma 1 and gamma 0, or gamma 2. And that's exactly what we see on the plot. There is one peak that corresponds to one resonance, another peak that corresponds to the second resonance, and you see that they're interfering. So we also should treat it further when we will try to feed this data. To feed the data, we will parameterize it using K-matrix approach. As Nils already introduced to you, K-matrix generally defined as this, with two couplings that show the strengths of the coupling between different particles, and at the bottom we have mass of the resonance and mass of the system. In this case, we will not consider non-poles, only poles that have here, but as you saw in the Nils presentation, in Nils talk, there might be another polynomial here which represents non-pole states. We will consider only poles. And then K-matrix can be put into T-matrix, and T-matrix is a transition matrix that later can be used for cross-section calculation. So let's add some code here as well. So first of all, we need somehow introduce our two-body channel. So let's create a structure that's called two-body channel. And it will have two fields, let's call it MA and MB. So with this structure, we'll describe our two-body scattering of two particles A and B. For K-matrix, we can do a similar thing. Structure called K-matrix. This structure also will have some dimensions, N and V. So dimension N is the number of channels that we have here, and dimension V is the number of poles. And the field that we will have here is the poles of this K-matrix. So poles will be stored as a vector, and also these poles will have parameters of the pole, so mass and G values. Okay. So that's our K matrix structure. Okay, K matrix is ready. Let's introduce constructor of the K matrix. It will be a function called K matrix that takes poles as an input. Then we also should extract the dimensions of the K matrix from this pole. So these numbers V and N. As I said, V is just a length of the poles, so number of the poles, and V is a number of resonances. So yeah, number of channels. So we can take one member of this poles array and calculate the number of G values there. So that's basically will give us the number of channels, and then we should also extract poles itself. So I'm not giving you too much details. So on Julia process, what I'm typing here, we focus here on physics. So just quickly preparing all the interfacing things. So mass should be just a mass of the pole that is stored in the poles that we provide, in the name tuple that we provide, and also G values. They're provided also as a vector. This output, it should be the S vector of dimensions of the number of poles, because we extract some poles. And that's basically all. We just have to return this K matrix with all dimensions that are correct. So now everything should be right. So we prepared our K matrix, we prepared a function to construct it. And also final thing for K matrix that I want to show you is the way to provide amplitude for it, to calculate amplitude for it. So for amplitude, we'll need K matrix and the mass. And then we'll just apply basically this formula for K matrix. We'll just sum over all elements, different couplings. Sorry, I lost my pointer. Yeah, and divide by the difference in the masses of the system and the energy. And we are doing this for all poles, so for all masses and JS in the poles of our K matrix. Good. So we have this function for amplitude. Now we can move to the construction of the T matrix. So let's copy what I already put here, just to save some time. So this will be T matrix. Again, the dimensions for T matrix will be the same, since T matrix is dependent on the K matrix, but instead of poles, here we'll have this K matrix. Let's call it K. And else, what is important here is the number of channels, which will be again S vector, but this time it will be S vector of channels, not the poles. So dimension here will be N. And also the amount of channels is coming from two-body channels, so it will be N two-body channel structures stored here for the T matrix. Okay, so let's see what we have here in the formula for T matrix. So K matrix we already have. We also need to introduce phase space rho, which is diagonal matrix. Let's introduce a function that calculates this phase space. So it will be two-body channel as an input and the mass. And then we'll just use chaining function basically to calculate this phase space. So it will be mass of the system minus sum of the masses of our initial particles. MA and MB. Then we should multiply it by the M plus MA plus MB, and finally multiply by M squared minus MA minus MB squared. So in general, as you can see here, this phase space might be a complex value if mass of the system is below the threshold. In our case, it will be above the threshold, so everything will be fine. And also we should calculate this bracket here, which is used for T matrix. Let's call it D matrix as here, and introduce the function for the T matrix. So to calculate T matrix, we will use as an input our T matrix. And also a mass. First of all, we need to introduce identity matrix. So let's call it PD1. Which is identity matrix of dimensions and n. So number of channels. Then we should calculate this term, ik rho. Let's call it like this, I rho vector. Should be one imaginary one multiplied by rho. So function rho we already have. Then we use as input this T matrix. So we can extract number of channels from it. And also put this mass into the function of rho. And finally, multiply it by this identity matrix to make it diagonal. And finally, we can calculate D matrix. 1 minus A multiplied by I rho and V. So this vector of rho. So this is our D matrix. We don't need this constructor for the K matrix here. We can also introduce another function for the amplitude calculated based on the T, using basically this formula here. It will be quite simple. So just T matrix is an input. Then we should invert D matrix. And that's basically all. We just should it also multiply by another K matrix using the function for the amplitude that we already have. So see, basically we're doing the same what is written in this formula. We just calculate D matrix, invert it, and multiply by K matrix. So let's move further. We introduced already a two-body channel, K matrix, T matrix, and now let's compare what we have here, this flat A formula that is already introduced to you with the Bright-Wigner. And as you see, they're indeed quite similar to each other. Only differences we have that instead of M0, gamma 0, here we have these G values and phase space. So if we'll compare the denominator of these two formulas, we basically can see the pattern how to extract the widths from it. And indeed, we can estimate widths using this formula where we sum over all channels squared G values multiplied by the phase space and divided by the mass of the resonances. And other way around, if we have our data sample that we saw at the top with the histogram where we have these two peaks, knowing the widths of these peaks, we can also estimate our G values that we can further use for the fit. In our case, it is a little bit more simpler because we don't have many channels. We have only one channels and two resonances. So the widths of our resonances will be directly correspondent to these G values. And then final thing here in this part is a cross-section calculation. So basically, Elsen is already introduced to you this formula. I will just repeat it. That the main thing that we want to get is a cross-section, or other words, intensity, and it is defined with this formula using T matrix. J here is a flux. Further down, I will set this flux to 1 for simplicity, and we'll use word intensity instead of the cross-section. But here is a general definition of the cross-section. And also here you see the phase space. So let's move to our example that we are considering today. As I already said, that we looking into the data that was generated using this example where we have two channels one channel with two resonances, M1 and M2. And in this case, our K matrix would be just a scalar instead of matrix, which sums two different resonances. And then finally, we can introduce this T matrix again using K. In this case, it will be super easy. But what we will consider below is a production amplitude that Elsa Niels introduced to you at the end of his talk. And this production amplitude is basically super similar to the K matrix, but instead of the matrix, it is a vector. In our case, it will be a vector with two values for two resonances, and similar thing to the G values in K matrix. Here, these alphas, which are called production factors, which in general might be complex. And this complexity of this production factors will introduce the interference in our example. So that's basically the schematic representation of what we're looking into. So let's define production amplitude. Since time is running out a little bit, I will just copy the definition of the production amplitude, which is super similar to the T matrix. So here you see that we have production amplitude also with dimensions NV in the structure, which takes T matrix as a field, and also these alpha poles. So poles with alpha production factor, and then simple constructor for this production amplitude, and another function for the calculation of amplitude using this formula. So again, we use T matrix that we already introduced and multiply it by the P vector, which we takes from the poles of the T matrix, and then multiply it with the alpha values. So let me quickly clean it a little bit up because I'm not using these phases here. And I think it should work. So we have our production amplitude, and also another service function that we will need later to calculate the intensity of each resonances. So this amplitude that we defined here will give us total intensity for the whole system. Now, so we can access each resonance separately. For this, we need this service function called production pole. And finally, let's introduce a function called intensity, our main function that we'll use to build the spectrum. So it will take a model that we will create in a few minutes as an input, calculate the amplitude based on this model. Then we also need a phase space. Do you remember from the function for the cross section, which is just a row? From the model, which is in our case is a production amplitude. So we have there a field T matrix, extract T matrix. From T matrix, we can extract channels that we need to put to the phase space function, and also mass, and multiply by another mass, and return absolute squared value of the amplitude, basically absolute square value of the T matrix, and multiply it by the phase space. As I said, flux in our case will be just put 1 because we'll look into the intensity, not the cross section. Okay, so we're moving to something real. Finally, let's construct the model for our case. So let's define the T metric first. As I said, we have the example with only one channel. So our vector for the T matrix will be just 1, 2 body channel. Type it here. So masses of our initial particles are 1.0 and 1.0. So for example, you can think about this as a scattering of 2 protons. And our poles are following. So mass of the first resonance, and then GS. I'll just copy the formula for it. So as you remember above, I show you how to estimate the G values using the widths of the resonance that you can guess from the spectrum. So then you can use this formula. And we have 2 resonances, so we also should introduce the pole which corresponds to the second resonances with mass M2, and of course with the width gamma 2. Okay, we have our 2-body channel, we have our poles. We can now initialize K matrix using the constructor that we defined, and also T matrix. I think that's all. Good. We have our T matrix. And now we can use this T matrix to calculate, to initialize production amplitude. So this is production amplitude. And then we just use this T vector and S vector, which in this case contains our production couplings alpha. So in our example, first production coupling will be real, alpha 1. And for the second production coupling, we'll have also the phase phi 2, which we will define with this slider. So all parameters we'll define in a few minutes. And in order to define these parameters, let me skip typing of this plotting. So I will just copy it and paste for us to faster see all the nice pictures here. Yeah, sure. I forgot to introduce K matrix here. So K matrix, we can define it using basically this amplitude. Yes. So now we see this nice plot, but as you can see, our parameters are completely off now. So we should guess to estimate them, and we can do this based on our data. So for example, for first resonance, we see that mass should be somewhere at 4.4. Mass of the second resonance somewhere at 6.1. Now we can also guess widths. So for the first resonance, we can do this on the left shoulder of this resonance. So it would be something like 0.8. And for the second resonance, would be something, I don't know, like 0.9. Let's put it to 0.9. And now we should also pull up these resonances using production couplings. So something like this. Yeah, maybe we should move second resonance a little bit to the left. But first, let's introduce interference, because now our phase is 0. We'll increase it. You see, now we only guessing this, by guessing these parameters, we almost fit this data. So now let's really fit it. For this, first we should introduce function build model. I will just copy it because it's basically the same that we already did, just in steps. So here our build model takes as an input parameters that we defined here, and then does everything that we already did. There is channels, poles, construct K matrix, T matrix, and finally production pole, production amplitude, and returns production amplitude, which basically is our model. And else I will copy the function for the fit as we're running out of time. So it's basically something standard as in any framework that you can find. So this is our fit. We initialize initial parameters. This is something service. Don't pay too much attention for this. Our data is taken from the input data, which we defined initially as errors from there. And then our model will be just defined by the build model function that we just introduced. And finally, what will be used for fitting is intensity, which calculated based on this model. And our objective will be just a chi-square, which is the difference between the data points and our fit points calculated with intensity and divided by the errors. So I will fit it with using optimize function of the package called optim in the Julia. You can do it with whatever you want, whatever programming language you're using, whatever framework you're using. And then we will extract our best parameters based on the fit result. Okay, let's do it. Somewhere we got complex value. Let me think how we quickly can fix it. I think it's in our intensity. We can just put it to real. So another thing that we can do is to introduce complex masses here to body. Okay. So we have success here. This is our final chi-squared value. Should also divide it by 40 since we have 40 bins. So by the number of degrees of freedom. So it's below 1, which is quite good. And this is our best parameters, best fit parameters. So masses, widths, and alpha couplings. And let's plot this result. So I'll just copy again the plotting, which is basically the same as we already did when we guessed our parameters. But here we first need to introduce model for our best parameters and then plot everything for it. So we see how smooth our fit function is. We fit our data points. So that's basically all that I wanted to show you today. And just as a brief summary, as you remember, initially we just had the bare data points, and we guessed everything and fit it quite fast, just using the K matrix approach, which is quite powerful. And you can use it in your analysis if you see this relevant to your case as well. So thank you very much for your attention. Sorry for being a little bit late.